Hello students, welcome to this lecture. In last few lectures, we have been discussing variational principle and in particular the linear variational method. We have seen how we can work out linear variational problems. Now in this lecture, we would apply linear variational principle in one of the most important topics in chemistry, that is in chemical bonding. Our first example system is a hydrogen molecule. In fact, we are going to discuss the valence bond treatment of hydrogen molecule, the simplest of the systems where a chemical bond is present. Now, when I look at the system, I have the Hamiltonian over here, which has got the kinetic energy of the nuclei, the kinetic energy of the electrons, the interaction of the electron with the nuclei, electron-electron repulsion and the nuclear-nuclear interaction. So, these terms are present in my Hamiltonian. Of course, I know because of this presence of 1 over R12 term, I will not be able to solve this problem exactly. That is the reason why I am using one approximate method to obtain the solution of this problem. Now, in linear variational problem or in general in variational method, the first step is to make a trial function, make a guess for your wave function. So, that is the trial function. Now, since I am talking about hydrogen molecule, which is composed of 2 hydrogen atoms, I call them A and B. The natural choice of the trial wave function would be the product of these two 1s orbital of the 2 hydrogen atoms A and B. This wave function that I am showing as phi 1. But the trouble with this function is that as long as the 2 hydrogen atoms are far away from each other, it is alright because each system has 1 electron. So, there is some idea about the identity of the electron. However, when the 2 atoms start making a bond, in that situation, the electrons are now, they belong to the molecule. Now, it is no longer possible to identify the electron with respect to their original nucleus. Once the molecules start forming, once a bond starts forming, the electron belongs to the molecule. So, we have to incorporate the so called indistinguishability of the electrons. How would I do that? The easiest or the most straightforward way to introduce this indistinguishability to the problem is to define another wave function phi 2, wherein I put electron 2 into nucleus A and electron 1 in nucleus B, and I mix this phi 1 and phi 2 by making this trial wave function phi as a linear combination of phi 1 and phi 2. Now, you would see that the trial function phi has the required condition of indistinguishability of identical particles. So, the C1 and C2 that you see here, they are the amplitudes or the coefficients of phi 1 and phi 2 to the overall trial function. We already know the form of 1s orbital of hydrogen atom. So, therefore, the phi 1 and phi 2 are kind of known functions. What are unknown here in this trial function is the coefficients C1 and C2. So, that means how these 2 hydrogen atom wave functions are combining, or to what extent they are combining to give me the wave function for the hydrogen molecule. These are the questions, that is the question that I want to answer. Now, the moment I see that the trial function is a linear combination of 2 functions, I already know that to solve this variational problem, I have to look at this 2 by 2 determinant. Now, this has got several terms, the overlap integrals S11, S12, S22. It has also got the energy integrals H11, H12, H22. What we do now is evaluate these integrals, because the moment we evaluate these integrals, we will plug them in this equation and you will immediately get the energy value as well as the coefficients C1 and C2. That means we will get the eigenvalues, the energy of the states and the wave function of the states. Only thing that is stopping us to do is that to get this overlap integrals and the energy integrals. Now, let us try to do them. First, we will discuss the overlap integrals. Just to remind you, my trial wave function phi 1, phi 2 are given here, and the trial wave function is C1 phi 1 plus C2 phi 2, where phi 1 and phi 2 are shown here. just we discuss them. Now, the overlap integral is obtained by evaluating S11 is obtained by evaluating the overlap of phi 1 with itself. When I do this, I have this overlap integral written in bracket form. So, then the bra side I have phi 1, ket side I have phi 1, and I open them up and write them in integral forms. That is because I see that there are some functions which depend on electron number 1, and there are some functions which depend on electron number 2. Now, the variable of integration over here I am integrating over the coordinates of electron 1 and electron 2. So, therefore, what I am doing is that I am separating the functions that depend on electron 1 from those functions which depend on electron 2. I see that 1SA1 in the one term in the bra and another term in the ket, they have dependence on electron 1. So, I am integrating these functions with along R1. So, I have this integral. And the next integral is simply with respect to the second electron's coordinate dr2. Now, when I look at the first integral, what do I see? I see it simply overlap of 1s orbital of a nucleus with itself. Now, I know that hydrogen atom A, the Hamiltonian is a Hermitian operator. So, therefore, the wave functions are orthonormal. So, this is normalized. So, this value is 1. Similarly, for B nucleus also I get 1. So, therefore, the product of them is 1. Same thing I can show for S22, where S22 would be obtained by evaluating the overlap integral of phi 2 with itself. I would suggest you to please do that, so that you have the practice of writing down the functions as well as separating the functions according to their electron dependence and then evaluating those integrals. Now, what we do is that we would go ahead with the other integral, other overlap integral, that is S12, the overlap of phi 1 with phi 2, not with itself. So, now here S12 I see phi, in the bra I see phi 1 and in the ket I see phi 2. So, overlap of phi 1 and phi 2. Now, again I do the same thing, I collect the terms which are dependent on electron number 1. So, in the bra it is 1sa1, in the ket it is 1sb1. Now, I collect those terms, I write down this integral. When I see here, I see overlap of 1sa and 1sb, although they both depend on electron number 1, but mind you, so these are not eigenfunctions of the same Hermitian operator. 1sa is an eigenfunction of the Hermitian operator corresponding to the Hamiltonian of nucleus A. 1sb is the eigenfunction of the Hermitian operator, that is the Hamiltonian operator corresponding to the nucleus B. These are eigenfunctions of two different Hermitian operators. So, therefore, there the orthonormality that we discussed in some other examples would not be applicable here. So, they are certainly not orthogonal to each other, but they are also not necessarily normalized, because what happens is that one is individually they are normalized, but this overlap is also not equal to 1, because 1sa is centered around nucleus A, 1sb is centered around nucleus B. So, if the two nuclei are far apart from each other, the overlap of these two functions would not be there. So, this overlap integral will become 0. When the two atoms come closer to each other, this overlap integral will become larger and larger, and in those imaginary situations, when I put both atoms on top of each other, in that case 1sa and 1sb would simply kind of coincide. So, they will become the function of the same fictitious system. So, that overlap can become 1. So, what I just described is that this integral over here, it has got a finite value s, I call that s, and this value of s is a function of r, the internuclear distance. As r changes, the value of this overlap integral is going to change. That is because the overlap is a function of nuclear distances. So, if the nuclei are far away from each other, the overlap will become 0. If they are exactly on top of each other, then it becomes 1. So therefore, the overlap varies from 1 to 0 in some form. The exact form can be actually evaluated for 1s orbital, but we should keep in mind that its value is the overlap integral varies between 0 to 1 based on the internuclear distance r. The second term, again similarly, I see the second integral contains the terms that are dependent on electron number 2. In the bra I have 1sp, in the ket I have 1sa. When I take this term, again this is an overlap integral which is neither 0 nor 1. It has a finite value and its value has to be evaluated for the particular distance that we are considering. Just to remind you, we are still working under Born-Oppenheimer approximation. That means our nuclei are frozen. So therefore, I have a fixed value of r. So given that I have a fixed value of r, I have a definite value of the overlap integral s, and therefore one term s comes from first integral, another term s comes from another integral. So I am writing it as s square. Similarly, I can show that for h21, which is the overlap of phi 2 with phi 1. So that's just the other way around. Now, after we have looked at the overlap integrals, now let us look at the energy integrals. Now, just to remind you, this is my trial function which depends on phi 1 and phi 2. To evaluate the energy integrals, we first look at the Hamiltonian of the system. In this Hamiltonian, I have discarded already the nuclear kinetic energy, because within Born-Oppenheimer approximation that is simply 0. I have got 2 electron kinetic energies shown by Laplacian, 4 electron nuclear interaction energy, 1 electron repulsion, 1 nuclear interaction. Now, what I am trying to do is that look at this total Hamiltonian and try to figure out some simple way of writing these terms. Now, the terms that you see in red here, this says the kinetic energy of electron 1 and its interaction, electron 1's interaction with the nucleus A. If these two terms I take together, it would simply remind me of hydrogen atom A that contains electron number 1, because it has got kinetic energy of electron 1 and its interaction with nucleus A. So this is hydrogen atom A, or I am calling this H1. This little h that I see is the Hamiltonian of one hydrogen atom. Now similarly, I can collect these two terms, the kinetic energy of second electron plus its interaction with nucleus B. If I combine these two terms, I would get the Hamiltonian of hydrogen atom B. I am calling that H2. Now H1 and H2's solutions are known. What are they? When H1 acts on 1sa1, that is 1s orbital of a nucleus, it gives me energy of minus 0.5 in atomic units. When H2 acts on 1sb, which is an eigenfunction of this operator, again I get the energy as minus 0.5 atomic units. So these two equations, these two relations I know because I know the solution of hydrogen atom. That leaves me with these four terms written in black. What are they? Electron 1's interaction with nucleus B, electron 2 interaction with nucleus A. Remember, these two electron nuclear interactions are absent when there is no chemical bond. That means if two hydrogen atoms do not know the presence of each other, electron 1 that is in with atom A doesn't interact with the nucleus P because it doesn't know the presence, it's not aware of the presence of nucleus P. So therefore R1b becomes 0 at infinity separation of nucleus A and B. Similarly, 1 over R2 atom also becomes 0 when the two nuclei are far away from each other. Again, 1 over R12, if the two atoms are extremely far away from each other, there is no electron-electron repulsion, neither is there any nuclear-nuclear repulsion. So these four terms that we see arise when the two hydrogen atoms start interacting with each other, or in other words, when they start forming chemical bond. So therefore, these terms are important, or they are going to contribute to the chemical bond formation. Now, given the choice, the way we wrote down this Hamiltonian, now we'll try to evaluate the matrix element H11. That is, in the left bra side I have phi 1, the ket I have same phi 1, and the Hamiltonian I just wrote down this Hamiltonian that I simplified. Now, I have to evaluate this term. So, let us first look at this H1 term operator. H1 operator, when it acts on this ket state on the right hand side, it sees that 1SA1 is an eigenfunction of this state. So, when H1 acts on 1SA1, it gives me minus 0.5 1SA1, and in the bra I already have 1SA1. So, then that term will give me minus 0.5 into 1SA1 and 1SA1 overlap. So, that will give me simply minus 0.5. That is for the electron number 1. Now, in the same Hamiltonian H1, I would also have this 1sb term, because they depend on the electron number 2, whereas the operator H1, the red one, depends on only electron number 1. So, therefore, I have this overlap integral over here, which I know as 1. So, therefore, this term becomes 0.5. I do the same for the second term H2. I see that the expression H2, I see 1sb2 in the ket is an eigenfunction of H2 with an eigenvalue of minus 0.5, and then when I do this I would get minus 0.5 into 1. So, this term gives me, H1 term gives me minus 0.5, H2 terms gives me minus 0.5, because this integral and this integral are simply 1. So, together they will give me minus 1, minus 0.5, minus 0.5. Now, let us look at the other term. The other H prime has got 4 terms over here, the operator, and then I am now writing the full integral form. So, in the complex conjugate of phi 1 and complex as the phi 1 itself, and I am integrating it over R1 and R2. Now, I have got 4 such integrals. I will do that step by step. So, which is now these 2 terms h1 and little h2, they give me minus 1. And now, first I am considering the effect of this 1 over R1b. I will come to this remaining 3 terms in a moment's time, but first let us look at R1b. Now, when I see this operator 1b, it depends on the operator depends on electron number 1. So, I have to separate the terms that depend on electron number 1 from those terms that depend on electron number 2. Now, I am collecting all the terms that are depending on electron number 1. So, that is 1sa star 1, and from the ket I have 1sa 1 and the operator. Now, there is another integral, that is 1sb star 2 and 1sb 2, and I will integrate over dr2. So, that will give me 1, because that is the 1sb is a normalized function. So, therefore, the term that I am left with is essentially this term multiplied by 1. So, this term. Now, let us look carefully at this term. What does this integral tells me? I have 1sa star 1sa. If I multiply them, I get mod of 1sa square. That is, if you remember, the probabilistic Born interpretation of the wave function, that psi star psi corresponds to the probability distribution of that function, wave state function. Now, 1sa square actually gives me the probability distribution of this electron. Multiply that with a negative charge minus E, what I get is the charge distribution of electron number 1, because I am looking at this probability distribution corresponding to electron number 1. So, if I multiply this 1sa mod square with minus 1, that actually gives me the charge distribution of corresponding to electron 1, which is present in now nucleus A. Now, I see the term 1 over R1b, and that makes this overall integral as some sort of Coulombic interaction between the charge cloud of electron 1 with nucleus B. The charge cloud of electron 1 that is coming from the wave function 1sa mod square, and its interaction with the nucleus B. Why do I call nucleus B? Because I look at this operator, that is 1 over R1b. So, this integral is essentially a Coulombic interaction between the charge cloud of electron 1 with the nucleus B. Mind you, when these two hydrogen atoms were far away from each other, electron 1 wasn't aware of nucleus B. Now, because they are coming closer to each other, I have got this Coulomb type of interaction of electron 1 with nucleus B. So, this is one of those Coulomb integrals I call. Similarly, I can do the same analysis for R of 1 over R2a. I collect the terms that have dependence on electron 2, and I see this term corresponds to the charge distribution of electron 2 and its interaction with nucleus A. Again, electron cloud corresponding to electron number 2 and its interaction with nucleus A. This interaction is not there when the two hydrogen atoms are far away from each other. So, this is a manifestation of the chemical bonding, so to speak. The next term that we see can be expressed as charge cloud of electron 1 and charge cloud of electron 2, charge density of electron 1 and its interaction with the charge density of electron number 2, the Coulombic interaction between these two charge density distributions. And the last term is 1 over R1b, which is again a Coulombic interaction between nucleus A and nucleus B. What we see here, I got -1 plus there are 4 terms which are some form of Coulombic interaction. Electron 1 with nucleus B, electron 2 with nucleus A, electron 1 with electron 2 and nucleus A and nucleus B. So, these 4 integrals together are called Coulomb's integral. So, I write this now -1 plus j, I call that as a Coulomb's integral, and this Coulomb's integral, the exact value of this integral depends on the internuclear distance, because the moment you make R infinite, all these terms will vanish. As you bring the two nuclei closer to each other, that means some finite value of R, the effect of these interactions will be experienced or will be felt. So, this Coulomb integral is a function of R. Exact functional form of Coulomb interaction, it is possible to get an idea based on the wave function that we are getting, but we will not bother about that. We will simply say that as capital R, the internuclear distance increases, the Coulomb interaction keeps changing. Okay. So, this is about H11 or even H22. Now, what we do is that we will evaluate the other term, other energy integral, that is H12. But just before that, we need to do some little adjustment, or not really adjustment, a rewriting of the Hamiltonian that we have here. So, this is the Hamiltonian that we have, the terms you are all familiar with. Simply the coloring has changed a bit. What I have done is that I am considering the kinetic energy of electron 1 and taking the interaction of electron 1 with nucleus B. Now, I am putting these two terms together, making this red Hamiltonian H1, that is the Hamiltonian of hydrogen atom. But now, this hydrogen atom, mind you, has electron number 1 with nucleus B. Now, in that case, the this Hamiltonian H1, so eigenfunction would become 1sb, because the electrons are indistinguishable. I have this 1sb is simply the 1s orbital of B nucleus. How would I distinguish that? Because if I consider 1s orbital of A nucleus, that is centered at the 1s at A nucleus. If I am considering 1sb, that orbital is centered around B nucleus. So, therefore, H1, since now H1 contains the interaction with nucleus B, so therefore, I am giving 1sb as an eigenfunction to this H1. In that case, the 1sb1 becomes eigenfunction to H1 Hamiltonian with eigenvalue -0.5, and similarly, I am taking kinetic energy of the electron 2 and its interaction with nucleus A. So, now this green H2, the green Hamiltonian, has eigenfunction as 1sa carrying electron number 2, and it would give me eigenvalue of -0.5. Now, that again leaves me with 4 different terms. Of course, you know Coulomb interaction, repulsion between the 2 electrons, interaction between the 2 nuclei, and these 2 terms. What are they? -1 over R1a and -1 over R2b. So, these are 2 electron nuclear interactions. Now, using this form of the Hamiltonian, we are going to evaluate H12. You might be wondering why would I do such a little exercise. You would see normally what would happen is that since I am going to evaluate an integral over phi 1 h phi 2, so the Hamiltonian will act on phi 2. So I look at this phi 2, the functions that are present in phi 2, and try to reformulate my Hamiltonian such that the such that my exercise becomes slightly simpler. So this is what I do here. I wrote down the phi 1, phi 2 in the bra and ket, the Hamiltonian over here. So the first term H1, let us look at its impact. H1 when it acts on 1s B1 gives me minus 0.51 1s B1, and then I have simply that 1s B1, I am evaluating the integral with 1s A1 because I am collecting all the term with that depends on electron number 1. But I still have terms that are dependent on electron number 2. Since the operator H1 does not have electron number 2 dependence, so therefore I simply have two functions that have electron 2 dependence, that is 1s B, 1s A. So I wrote them 1s B, 1s A. I know that this is an overlap integral S. So this is also an overlap integral S. So the first term gives me minus 0.5 S square. Similarly, the second term gives me also similar value, that is minus 0.5 S square. So here H2, the second Hamiltonian, acts on 1SA2 because that is the eigenfunction. Here I have written down, and then when it acts I have minus 0.5 multiplied by 1SA2, and I have bra function has 1sB2. So again I get an overlap function S, and I collect the terms that have only electron number 1 dependence. So that gives me another S. So this is again minus 0.5 S square. So together these two terms is minus S square. Now I look at the next term, that is H prime. So all these 4 terms I have written down, and in the bra I have 1s the phi 1, in the ket I have phi 2. The first term is simple, the sum of this red and green term minus S square. Now let us, just like the previous case, let us look at this minus 1 over R1a term, part of the operator. When I do this, I see I collect, since the operator depends only on electron 1, I collected only the terms that have electron 1 dependence and integrate it, and separately integrate the terms which have electron number 2 dependence. Now when I look at this term, in the previous case when I was evaluating H11, I had a simple description of this matrix element. What was that? I called it the charge distribution of electron 1 and its interaction with nucleus B. That was a Coulombic interaction. But here you look, I do not have that kind of interpretation. Why? Because in the left hand side I have 1s A star, right hand side I have 1s B. So electron 1 is now in left hand side nucleus A, electron 1 in the right hand side is in the nucleus B. So that bond interpretation that I used in the previous time, I cannot use it here because the two functions are separate. So what actually does this represent? This does not have a physical explanation. I cannot explain you in pure words as to what this expresses, because this is a purely quantum mechanical formulation. Why is it happening? This is happening because in our wave function we have exchanged the electron. We have constructed this phi 2 which takes care of the exchange of the electron 1 to nucleus B, electron number 2 to nucleus A. So because of this exchange term, I am getting this extra integral which does not have any classical description. This is a pure quantum mechanical origin. And similarly, I can show it for the rest of the terms. All these terms, unlike the previous case, do not have a physical interpretation, and all of them they appear because in my wave function I have a term that exchanges the two electrons. So together I call them minus S square plus some integral, I call that an exchange integral K. Again remind you, exchange integral does not have a physical interpretation unlike the Coulomb integral J, and just like J, exchange integral K is also a function of the internuclear distance. As you increase the internuclear distance, the value of K keeps changing because at infinite separation the K does not exist because the two atoms do not know each other, so there is no exchange of electrons, so therefore exchange integral is also 0. But as soon as they come closer, the exchange integral takes over and it starts appearing, and then it influences the chemical bond. So now so far what we have done in this lecture is that we have calculated the matrix elements, the energy integrals, the overlap integrals. Now what we have to do is that we have to plug them in our 2 by 2 determinant and go for the solution. But this part we will do in our next lecture. In this video, we started discussing the application of linear variational method to chemical bonding. So far we have discussed the valence bond treatment of hydrogen molecule. We have derived the expression for the energy integrals, overlap integrals. How we use them to get the final results is the topic of our discussion for the next class. Thank you for your attention.